Alright, we have different types of eruptions depending on what our magma is made out of and depending on what type of volcano we're looking at. So how are the four types of eruptions on this image different from each other? So the first one we're going to look at is a lava flow. A lava flow is low viscosity lava that flows for great distances. Low viscosity lava that flows for great distances. Okay, so basically what that means is it's runny, it moves like almost like water, it's very fluid, and it can travel a long way. Okay, so in this image we can see it sort of pouring down this stair-step mesa here and just flowing along, doing its thing. So low viscosity lava that flows for great distances. In contrast, you can have a lava fountain Okay, in this one we've got, I'm sorry, on your notes I wrote lava eruption. So we're going to consider that the same. The actual feature is called a fountain. But when lava is erupting, it can erupt as a fountain. So higher gas content leads to explosive lava fountains that spray out of the vent. Higher gas content leads to explosive lava fountains that spray out of the vent. Okay, so you get a buildup of pressure from these gases, and it just projectiles this lava out of the vent, and it can reach pretty high up. Alright, the next one is the dome. So a dome is a high viscosity lava that does not flow easily. A high viscosity lava that does not flow easily. It piles upward, making unstable slopes. Okay, so you get this big mound of stuff that's not very well held together, and it's unstable slopes, meaning it's easy to have little or actually gigantic landslides if that dome gives way. And the last one here is the eruption column. And this is a big eruption of ash, gas, and volcanic matter that gets shot high into the atmosphere. A big eruption of ash, gas, and volcanic matter that gets shot high into the atmosphere. Okay, so these upper two photos here, the lava flow and the lava fountain, are both showing us a mafic lava. Okay, so they're both dark colored rocks that result. They're both low viscosity. And then the bottom two images are both felsic. So higher viscosity, lighter colored rocks, and more explosive results. Okay, I have some videos here of what a lava flow looks like, what a lava fountain looks like. We've already seen how a dome gets built with that cool time-lapse video, but this one shows you what happens when it collapses, which can be really devastating. And then the last one is the eruption column. How do gases affect magma? So the first thing I want you to think about is a soda or any sort of carbonated beverage. What happens when you open a soda that has been shaken up? Okay, you make a huge mess, right? It explodes. You get soda everywhere. So why does that happen? It happens because we've got gas in the soda, right? So where does the gas come from? The gas comes from the soda. It is dissolved in the liquid because it's pressurized. So when you release the pressure from the lid by opening up your soda, the pressure allows the gas to form. Okay, so I'll repeat that again. While it's in the soda, the gas is dissolved. When you open up your soda, because you release the pressure, then it is allowed to turn into gas form. Okay, so it's the exact same thing that happens with volcanoes. We start out with dissolved gas held in the magma by pressure. Okay, so how is magma like soda? Magma contains dissolved gases such as water vapor, carbon dioxide, and sulfur dioxide. Magma contains dissolved gases such as water vapor, carbon dioxide, and sulfur dioxide. Okay, under less pressure, gas bubbles start to form. So as that magma works its way up toward the surface where it's under less and less pressure, now we get gas bubbles forming. Okay, and it's those gas bubbles that pop and build up pressure and propel the eruption to form to form ash. Okay, so when you have all of these bubbles building up and reaching the surface, they pressurize and create an explosive eruption, pulverizing the rock into ash. All right, that takes us to the next question in your notes. What is viscosity? Viscosity is how easily a liquid flows. Viscosity is how easily a liquid flows. Okay, so if it is more viscous, it's difficult for it to flow, and it traps gas. If it is less viscous, it flows easier and gas can escape. Okay, my best example in real life here has to do with making spaghetti. So when I'm making spaghetti sauce, it's thicker than the water that's boiling for me to cook my pasta, right? And so when I get a gas bubble in my pasta sauce, it splatters everywhere. I burn myself and make a big mess. There's pasta sauce spatters all over the place, right? That's because it's in a more viscous fluid. Whereas when I'm boiling the water for my pasta, the bubbles just move out, no problem. There's not a lot of spattering because it is less viscous. The water is less viscous than the pasta sauce, so it's easy for the gas to just release as the boiling bubbles. Okay, that's my real life example. In the case of magma and lava, what we're talking about is the composition. So the viscosity in the magma is controlled by the amount of silica. The viscosity in the magma is controlled by the amount of silica, and that is SiO2. 1 silica and 2 oxygens, SiO2. The more silica, the higher the viscosity. The more silica, the higher the viscosity. All right, your next question, how does viscosity affect the gases in magma? Well, if you want to, you can go ahead and take a look at these videos here to show you what happens to the gas in magma once it reaches the surface, depending on the viscosity. So the top one is showing you a more explosive eruption of what happens when gases get built up because the magma is too thick to readily release the gas bubbles. So you just build up tons of pressure and then end up having an explosive eruption. versus the less viscous lava, where bubbles are just able to work their way to the surface, and because the lava is less viscous, because it's thinner, it's easier for those bubbles to be released. So go ahead and take a look at those videos so you can see what it looks like, but just to tell you how does viscosity affect the gases in magma. Gases that form want to escape to the surface. If the magma has a high viscosity, it does not allow the gases to escape easily, leading to explosive pressure. Okay, one more time. Gases that form want to escape to the surface. If the magma has a high viscosity, it doesn't allow the gases to escape easily, leading to explosive pressure. Okay, and so the last question here is building on that information. Which type of viscosity, more or less, will create an explosive eruption? It should be more. Gases get trapped and pressure builds up until it is greater than the friction and the volcano explodes. Okay, gases get trapped and pressure builds within the magma chamber until the pressure is greater than the friction and the volcano explodes. So some other examples in real life, things that would be more viscous. We can think about peanut butter or toothpaste or cold molasses. Things that resist flow are more viscous. Okay, less viscous would be water or any sort of liquid, or hot maple syrup versus cold maple syrup, which would be more viscous. So it has to do not only with composition, what it's made of, but it also has to do with temperature. So as you increase the temperature, you can create less viscosity. Alrighty. Scoria cones and basalt flows. What are the characteristics of a scoria cone? Okay, it is going to be small in size. It will have lava flows and cinder ejections. That means it's throwing out little bits of ash and tiny rocks. When we're looking at this lava fountain here in the image on the left, that's what's going on here. It's just throwing out little bits of lava that solidify in the air and they fall down like a pile of rocks. Okay, so it's small in size. We can have lava flows and cinder ejections, and this is a low viscosity lava. A low viscosity lava. The type of rocks that will form are vesicular basalt. Vesicular just means it has holes in it. We call holes in rocks vesicles. Okay, so vesicular basalt, non-vesicular basalt, which most people just call basalt, doesn't have any holes in it, and then scoria is the bottom image there. Okay, so vesicular basalt, non-vesicular basalt, and scoria. These are all mafic rocks. They're all very dark, lower density rocks. Alright, so that gets us into talking about magma composition. We were just looking at scoria cones, and these are basaltic lava flows, right? So they've got low viscosity, they have dark colored rocks because they are mafic. So what the heck does that mean? You don't have this image in your notes, but it would be really easy for you to just flip your page over and sketch it out, because this is a simple image that's easy to refer back to give you an idea of what I'm talking about with felsic and mafic. So again, felsic and mafic are just terms that describe a magma composition, meaning what is it made up of, what is it composed of, what is the recipe of minerals that makes it what it is. Okay, so you can think of felsic like the opposite of mafic, and in between those two we get what we call intermediate, which is just a mix of the two. Okay, and I've split this into extrusive rocks, which are rocks that are erupted onto the surface, and intrusive rocks, which are rocks that solidify at depth. Okay, so we're going to start off on the left with felsic. Felsic is characterized for being light color. It is a high viscosity because it has a high silica content, which is that SiO2. And this usually forms on the continental crust. Okay, because continental crust is mostly SiO2. It's mostly silica. So if that felsic magma cools off at depth, we're going to have great big crystals because it's cooled slowly and crystals take time to grow, and we're going to form granite. If instead of cooling off at depth, this magma gets erupted out onto the surface, the type of rock that will form is rhyolite. Okay, and the point of me putting them in this format is so that you can see that granite is the exact same composition as rhyolite. The only difference is the cooling time. Okay, granite has ages to cool off and form great big crystals. Rhyolite cools very quickly because it's erupted onto the surface. Okay, on the opposite end of our spectrum here, mafic rocks are going to be dark colored, lower viscosity, because they have very little silica content, and these are usually associated with oceanic crust. Okay, the oceanic crust is mafic. So the rocks that will form are intrusive rock if the mafic magma chamber just sits there and cools off over time. It will form the rock called gabbro. If that instead of cooling erupts out of a volcano, that will solidify to be basalt. Okay, so the entire ocean floor is made of basalt. All of Hawaii is made of basalt. Anytime you're just dealing with oceanic crust, we're talking about basalt. Okay, that is the rock name. It's the most common rock on the planet. And then if we combine those two, we get intermediate. So the rock types there, the intrusive intermediate rock is diorite, the extrusive intermediate rock is andesite, and so that's going to be right in between those two. It's going to be medium color, so it'll be gray instead of white like felsic or black like mafic. It's going to have moderate or fluctuating viscosity, and this occurs when we have a combination of continental and oceanic crust. For example, when an oceanic plate subducts below a continental plate and those magmas mix. Alright, so looking at some more mafic features, some features of lava flows. We get lava tubes, which are really cool. You end up having the outer shell cool off first, and the lava that's still hot flowing through the center. And you don't have this in your notes, but this is building on what are characteristics of basaltic lava flows. Okay, so we're still there in your notes. So we get lava tubes, we get flows. Is a very chunky, steep slope forming lava, and that is a Hawaiian name. And the way that I remember that name is that if I were walking over it, because it's very angular and sharp, I would go as I walked over it, right? So that's how I remember. That's lava. As opposed to pahoehoe lava, which is a ropey, fluid flow. It's a very different type of flow, but all of these are mafic, right? They're all forming these black rocks. They're all relatively low viscosity. And I've got some cool videos for these that you can check out. And if you're interested in this, if you just go to YouTube and look up lava flows, you could watch these all day. They're really cool, especially the ones where you can hear what the lava sounds like as it's forming and breaking and moving. It's pretty cool. Alright, so back to the notes now. How do scoria cones and basaltic flows form around the same vent? Right? It doesn't make a whole lot of sense to have a very fluid flow and sort of a gassy flow. How does that happen? So it happens in two stages. So the first stage is the early formation of a scoria cone. And then it switches over to lava flows. So you can think of this like your soda again, right? If you shake up your soda and you open it up, all of the gassy froth comes out first. Okay, that's analogous to the early formation of the scoria cone. It's going to be sputtering out all of the gas and rock that forms like a big pile of loose rocks. And then, okay, switch your brain back over to the soda. So what gets left if you leave the lid off of that soda, right? We've just expelled a whole bunch of gas. And if we leave it there for a day, the next day it's going to be flat. So it's the same idea. You get a early formation of a scoria cone, release all of the gas off of the top of that magma chamber, and then basically your lava is flat, right? We've expelled the gas, and now it can be a more fluid flow. So it's able to switch. After expelling its gas, it can have a lava flow. Okay, and so here is an image showing us what a scoria cone looks like, and here we're looking at a lava flow. Right, so we can have both of those types of eruptions around the same volcano. That takes us to shield volcanoes. Still dealing with mafic rocks here. What are the characteristics of a shield volcano? Okay, so in this one we're looking at the big island of Hawaii. And we have fluid magma from fissures and scoria cones. Okay, the actual island itself is made up of 3 large volcanoes and 2 smaller volcanoes. Mauna Loa is the world's largest volcano at 29,520 feet above the sea floor. That works out to 13,680 feet above sea level because it extends quite a ways below the ocean. Mauna Loa's spine is a fissure fed by dikes. So again, dikes are volcanic features where magma is just flowing vertically. Okay, Kilauea is the world's most active volcano. Its eruptions form linear fissures and they are fed by dikes. There are calderas in shield volcanoes. Commonly, they form from lava lakes that form and drain, or from downward collapse rather than from explosions. Mauna Kea is also currently active. That is the volcano in the background here. Okay, so this is an example of the crater and small calderas. So again, this is just from having a magma chamber below the surface, release all of its magma, and then the surface sort of drops down to fill in that cave. Here are 3 different types of eruptions from a shield volcano. So we're looking at a fissure eruption, a lava flow, and an eruption into water. So all of these three ways are how shield volcanoes erupt. And if we take a look at these images, what sort of viscosity are we dealing with here? Okay, we know all of the rocks are very dark colored. So they should be basaltic, and therefore they are mafic, so they're low viscosity. Right, just looking at the lava flow, we can see the lava is able to flow, it's able to be fluid, so that is a low viscosity flow. Okay, the last feature I want to talk about here is pillow basalt. This is the formation that you get when lava erupts into water. It forms these really cool rounded shapes that are called pillows. Okay, so that only happens when lava erupts into water. Okay, here are some side views, or semi-aerial views of two shield volcanoes. The first one is Mauna Loa in Hawaii, and the bottom one is a smaller shield that's just west of Phoenix. So, taking a look at these, especially Mauna Loa, look at where the cloud line is. Okay, this is an extremely high elevation feature, but because its slopes are so gentle, you wouldn't even think that. So very gently sloping, very high elevation. That's why these are overall the largest volcanoes. Okay, they cover a huge area. They can be very big.